Welcome back to our fast physics lessons for electricity and electrostatics. Last time we looked at static electricity. In this particular lesson, we're going to be looking at electricity as a current in a wire. We're going to explore ideas of resistance, potential difference and potential energy, and power. When an object moves in a gravitational field, it usually experiences a change in kinetic energy and in gravitational potential energy due to the work done on the object by gravity. For example, we saw last semester that we had to do work to elevate an object against gravity, and then that gave the object potential energy. That potential energy could then be converted into kinetic energy. When a charge moves in an electric field, unless its displacement is perpendicular to the field, the electric force does work on the charge. Work is done by the electric force. And so the change in the charge's electrical potential energy can be defined as the change in potential energy is equal to the negative value of the work that's done. This is the same equation that we saw last semester with regard to potential and kinetic energy with regard to gravity. So when this test charge is placed inside this electric field, the charge is going to move from position A to position B. And when it does so, its electrical potential energy changes. The change in electrical potential energy is equal to the negative value of the charge times the strength of the field times how far it's gone. So this is our equation to find our change in potential energy. Notice that if the potential energy is decreasing, then the field has done positive work. If the potential energy is increasing, then the field is doing negative work. It's just like when you drop a rock to the ground. Gravity does positive work, and the rock loses its gravitational potential energy. Let's assume we have a current in an electron beam in a cathode ray tube that is 6.2 times 10 to the negative 6 amps. We aim a beam of electrons at a screen. How much charge hits that screen in a time of 4 seconds? Now remember that current is defined as the number of charge carriers that pass through a cross-sectional area in a particular time. So our relationship is current is equal to the charge divided by the time. We can rearrange this formula to find Q, our charge. We simply multiply these two numbers together. This gives us a charge of 2.48 times 10 to the negative 5 coulombs. Let's take a look at a problem that involves the use of Ohm's law. Remember, Ohm's law describes the relationship between current, resistance, and potential difference or voltage. We can rearrange this to find current, voltage, or resistance depending on what we're given in the problem. Let's assume we have a potential difference across the terminals of a battery of 9 volts. We have a resistance within this circuit of 4.2 ohms. What is the current in this circuit? Current is equal to my voltage divided by my resistance. Giving us an answer of 2.1 amps. The relationship between power, potential difference, and current is that power is equal to the change in potential difference times the current. How much power is needed to operate a radio that draws 6.2 amps of current when a potential difference of 120 volts is applied across it? Power is equal to the change in potential difference times the current. And we get 744 watts. Resistance is how difficult it is for the charges to pass through a wire. One way to think about this is to think about how hard it would be for those electrons to travel through. How much effort does it take for those electrons to travel through the wire? Which would require more effort? Traveling through a short wire or through a long wire? The long wire would have greater resistance because it's harder for the electrons to travel through it. Which would have a greater resistance? A fat wire with a large diameter or a very thin wire? the very small diameter, the thin wire has more resistance. Resistance is also influenced by the material that makes up the wire, and it's also influenced by temperature. Hotter materials have greater resistance than cooler materials. If you look closely at an incandescent light bulb, you'll notice that it has two large wires that travel up from the bottom of the base of the bulb, and then there's a very thin coiled wire in the center. This long, thin wire has greater resistance. This increase in resistance causes the wire to heat up and to glow. You are now ready to take your Unit 2 Lesson 7 quiz. Be sure to look over your notes before you take the quiz. Then you'll be ready to move on and look at your next lesson as we explore circuits and Ohm's law in greater depth.